Thank you. So I want to talk to you today about the mathematics of Ingress, and I wanted to start off by thanking the person I collaborated with a lot of this on. She is Dr. Kim Roth. She's up at Juniata College in Pennsylvania. So just wanted to thank her for her help. And we're going to talk about what Ingress is. So if you don't know the game, that's totally okay. I will get you the basics. We're going to talk about what about this has anything to do with mathematics. We're going to talk about graph theory in particular, then move over to triangulation, talk about maximal fielding, then talk about some open questions that this leaves us with. So, Ingress is a cell phone-based augmented reality game. So a virtual reality game would be one where you're set up in a different world entirely. An augmented reality game is where they take the real world and put another layer on top of it. So the basics of Ingress is there are two sides, the enlightened and the resistance, and there are portals in the real world. So the idea is historical places, public art, libraries, transit station, things that are real world things are portals in the game. And we'll talk a little bit about what the story is. But so this is on my collaborator's campus. It's an eagle statue. It is a portal in the game. The goal is you interact with the portals in various ways. So you have to go out in the real world to play this game. You can't sit at home on your couch and play. You have to go stand within 50 meters of the portal, and then you can hack it to get gear. You can capture it. You can make it belong to your team. You can blow it up if it belongs to the other team, so that then you can make it belong to your team. You can link the portals together. And then if you link 3 of them together in a triangle, you've made what's called a control field. So in the game, the idea is that there are alien beings called shapers that have been interfering in or helping out humanity throughout our history. So the enlightened believe that they've been helping us, that they are supporting human creativity, that shaper influence is going to lead to the evolution of humanity. So when you make an enlightened control field, a green field, you are augmenting the shaper influence inside that triangle. The resistance think that, no, we're not really fond of aliens messing around with humanity, and that we would actually be better off without this. And so a blue control field protects the people underneath it from shaper influence. So the idea is we've got people out there playing Ingress. You play it on your cell phone. The app is called your scanner. It's what lets you see this world with portals and exotic matter and all of this stuff going on. XM is this energy that's given off by portals that is somehow changing the world and powers your scanner and lets you do things. That's the energy bar in the game, right? Portals are sites in the real world. By doing things in the game gets you AP, action points. So that's the points that you need to level up and do things like that. And then there's this other twist that fields are scored, these triangles that you make are scored by, the story is how many people are under that field. So you make a field in a high density area, you score more mu than you do if you make that same field in the middle of a national forest, right? More people in the city than, okay. Now, that's one of those places where, okay, this is a thing you download onto your cell phone. People take apart the APK, and there's a lot of things about the game that we know how it works. The MU calculation is mostly done server side, so we don't know a whole lot about how that works, but we'll come back to that later. But so we've got a couple of different things in play. The idea is the world around you is not as it seems. There's really all of this alien influence happening. Things around you are portals. There are 85 portals on the Jacksonville University campus. The mural in the hallway, the fountains along the walks, the horoscopic atom sculpture in the engineering pavilion out there. All of those and lots of other things are portals on campus. So it's kind of interesting. Google created the game in November of 2012. They didn't exactly expect it to take off, and it has. Millions of people play it. It's played worldwide. It is a global game. There are things that are done that are coordinated around the world. The way you connect a portal to another portal is you need to take a key from one portal to the other portal. And there's no way for me to virtually send it. You can't email keys to people. I can stand next to you and drop a key on the ground, and you can pick it up. And then you can take it with you someplace. So if we want to link from here to DC, someone here needs to take a key to DC, or someone in DC needs to bring a key to us. And so there's an entire network of people passing keys around the world to make these things happen. The other thing is that links can't cross. So if I want to link from here to DC, there can't be any portal links along that path at all. So linking from here to DC requires people to go blow up all the stuff between here and DC so that line can go through. There have been operations to cover the United States in one color or another, and they've made some decent progress one way or the other. I don't think we've ever seen it go all the way through. I was part of an operation that we covered most of the Atlantic Ocean. We linked from St. Augustine to France to Brazil, and which is about as long as links can be. There are various, and there's lots of other mechanics and things like that in the game that put limits on things in various ways. So it's this giant game. It's been going for just over 3 years. And in the process of doing this, and in some ways it's a pretty simple game. There are portals. You want them. You want to connect them up. But it opens up all sorts of questions. So you're standing in a place that has some portals. Maybe you're looking at the boardwalk that goes down to MSRI? The little signs on it that say all the nature things? A lot of those are portals. So there's a cluster of 8 or 9 portals along the boardwalk down to MSRI. Is there a best way to link them up? Well, okay, it's an interesting question, but you have to first of all decide, what do you mean by best? There are people who are really into doing field art things, to making pretty or interesting or beautiful or, that definitely does look like a horse, arrangements out of portals. So that could be your metric for best. You could say you want to really defend one particular portal, and that would change what you mean by best. But let's say you are someone who's trying to earn points in the game. Every link you throw gets you points. So you have a cluster of portals. Is there a most number of links you can put there? Well, okay, sort of naively you could say, well, if there are some number of portals, I could link every single portal to every other one. That's not going to work because links can't cross. So there's a little bit of trickiness to it, but that was a question that came up and people were just asking as players. So if we have a particular grouping of portals, what is the maximum number of links? Is there a way to figure that out? And it starts, as a mathematician, that looks like a graph theory question. We have portals. So graph theory is dots, vertices, points that you've put down on the paper, connected up by edges. Ingress, we've got portals, our vertices, and we're connecting them up with links. Those would be our edges. And so started to think about graph theory sorts of things. And okay, you're looking at that one, and that's a perfectly good graph. That is not a perfectly good Ingress map. because some of the links cross. Links aren't allowed to cross, but we can have graphs where things aren't allowed to cross. Where if you can draw a graph so the links don't cross, it's called a planar graph because you can put it in the plane without the links crossing each other. Okay, so that one's not planar, agreed? At least not the way it looks right now. It is just because it's going to keep popping up. It's got 4 vertices, and every vertex is linked to every other possible vertex. Right? The one in the upper corner goes to all of the 3 others. Each of them goes to the other 3. So a graph like that is called a complete graph. And so the notation in graph theory is K4. It's the complete graph on 4 vertices. However, in graph theory, edges don't have to be straight. So a graph is planar if there is a way for you to draw it so that the edges don't cross. So rather than putting that line straight through the diagonal like that, you could draw it bent like that. Well, that works perfectly well in graph theory, but we're running into trouble with the analogy to Ingress because links only bend in Ingress due to the curvature of the Earth. Okay? So locally, if we're in a relatively small cluster, they need to be straight lines. So that's going to be a problem. The other problem that we run into is that in graph theory, you're allowed to move the vertices around. So all 3 of these pictures, while they look like different pictures, they are pictures of the same graph. So if you took this guy and scooched it into the middle and pulled the other ones around a little bit, we'd get this guy. So all 3 of those are the same graph, but we've just done things that you are not allowed to do in Ingress. So graph theory sort of was my hook into this where I started to look, but you really quickly realize that this isn't quite what we want. We really need our portals not to move because, okay, there is a process if a portal gets placed in the wrong spot to get it to appeal, to get it moved around, but that's not a normal part of gameplay. You can't just move the fountain outside down the street. Okay, so we need the portals to stay put. So there's a different branch of things that look at what are called point set triangulations. So a point set is a set of vertices with fixed locations. We like this better already, okay? So we've got our points, and you're not allowed to move them around. Which, I mean, you can think that that would make sense for other real-world applications, right? Anytime we're connecting physical things, we can't move portals around. We also can't move cities around, right? So, okay. A triangulation is you draw lines between the vertices until all you get are triangles. So we've got this guy over here. All of the regions in between them are triangles. So that is a triangulation of this point set. Is it the only possible triangulation of that point set? No, and that's what sort of sparked this question. You have a cluster of portals. There are lots of ways you could go about linking that thing up. Why are the triangles important? Well, we like to make triangles in Ingress. Triangles are fields. So this is fitting pretty well. Okay. We need some more vocabulary. A convex set is a set where if you take 2 points in it, the line you draw between them will stay inside the set. So what does that mean? Well, a circle would be a convex set, right? You pick 2 things inside it, the line you draw between doesn't leave the circle. How about a triangle? That would be okay. How about like a Pac-Man face? No, right? You could put one above the mouth and one below the mouth and the line would leave. So basically, for our purposes, what it being convex means is any angles you have need to point outward. So this irregular pentagon over here is convex, right? Okay. The convex hull of a point set is picture shrink wrapping your point set, okay? Pull in a convex set as small as you possibly can so that you still have the thing inside of it. So this is not only a convex set, it's the convex hull for this point set. Okay? So even if you picture your Pac-Man, you could shrink wrap that. It would be mostly round, and then you'd end up with a straight side covering up the mouth, right? Okay. So, like we said, there's more than one triangulation for a point set. Here are two possible ones. There are lots of others. So these are all ways that you could potentially link up your portals. How many triangles are there in this one? How many triangular faces do we have? 1, 2, 3, 4, 5? At least if we only look at the small ones. How about this guy? Also 5, okay. How many edges does it take to make this triangulation? I see 5 around the outside, 2 more to make the bigger triangle, and then 3 inside the big triangle. So we got 10. How about over here? Also 10, right? We got 5 around the outside and then 5 radiating from that middle point. Okay, that's only 2. Maybe I picked them out special. But you're starting to think maybe there is a pattern here, right? You link things up a bunch of ways and you go, huh, every way I've done it so far at least takes the same number of links. So the first thing that people guess is it depends on how many portals you have. So you start to draw some pictures. Well, with one portal, you're not making any links. 2 portals. There's only one way to link those guys up, and it's going to be 1 link. You have 3 portals. You can make 3 links that'll make a triangle, and there is exactly 1 way to do it. So far, I'm liking the pattern, right? We have a pattern. It depends on the number of portals. We get to 4 portals. If they're more square-ish or rectangular, the most links we can get in there without any of them crossing is 5, right? If we make them, if they're arranged as a triangle with a dot in the middle, we can get 6 links in there. So it depends on the number of portals, but it doesn't depend only on the number of portals. How they're arranged makes a difference. Okay, and so just as a sidebar, because we're going to come back to this again, notice that that arrangement is the only way you can get a K4 in the game of Ingress, right? If you have 4 portals arranged in another way, you're not going to be able to get all of the possible links in there. So just tuck that away for later. So let's go back to graph theory for a moment. One of the big results is Euler's theorem in graph theory. He had other theorems and other formulas. But what he wanted to do was relate the number of vertices, the number of edges, and the number of faces, the number of spaces inside a graph. Now, this doesn't work for just any graph. It needs to be connected, so it has to be all in one piece. You can't have a chunk over here and a chunk over here with no edges connecting them. It needs to be planar, so the edges themselves can't cross. Okay. And so he found out and proved that there's a formula that relates them, and it's the number of vertices minus the number of edges plus the number of faces is always 2. So we got a couple of examples up here. How many vertices over here? 4. With, we counted them before, 5 edges. How many faces? Okay, it is tempting to say 2, right? When we're thinking in terms of graph theory, we're thinking in terms of the entire plane. So there's 2 triangular ones and one that has everything outside the square, right? So We've actually got 3 faces there. Okay.
So everything outside of the square?
Everything outside of the square is also a face.
Think outside the box.
So think of not just what's inside the box, but if you had a giant piece of paper and drew this, you'd have a triangle, and everything outside. If you think about, using the bucket painting tool in Paint, if we wanted to color this whole background in, we'd have to do it once on the outside and then once in each triangle. So it divides the plane into 3 regions. So we've got 3 faces. And 4 minus 5 plus 3 is 2. Okay. All right, looking at this guy, still have 4 vertices. We'd counted off 6 edges already, right? 3 around the outside, 3 going into the middle. 4 faces, the 3 that are triangles and the 1 on the outside. And 6 minus 4 plus 4 is 2. Okay? So that's not a proof, right? That's just examples, but at least it seems to work. And there are proofs, and if you ever dig around in graph theory a little bit, it's not terribly hard to do, but it's sort of outside the scope of what we're going to do today. But think about our triangulations. Now, they're special. They're not just any planar graphs, but our triangulations are planar graphs, right? Are they connected? Yeah, because we haven't made all the possible triangles if they're not connected, right? So this guy should apply to our triangulations too. So there's a triangulation theorem, and this was known, this is out there in the literature, that if you have a point set that has n points, so n portals, n vertices, all of the triangulations have the same number of triangles, and we have a formula for it, and they have the same number of edges, where n is the total number of points in the thing, and k is the number of points on the convex hull. Okay, so it turns out those are the 2 things that matter. How many total portals there are, and how many portals make the outside wrapper for your cluster. Okay, so let's come back to our examples here. They're triangulated up in different ways, but in both cases, the total number of portals is 6, and the number of portals on the outside wrapper, the outside convex hull, is 5, right? So if we plug into our formula for t, the number of triangles, we're going to do 2 times n minus 2 minus k is 5. Any way you triangulate this thing, you end up with 5 triangles. We look at the edges, 3 times n, so 3 times 6, minus 3, minus k, so minus 5 is always going to be 10. Any way you triangulate this thing, it's going to take 10 edges to do it. So, how do we prove it? Well, it's just figuring out how to connect up the triangulation vocabulary with the Euler's theorem identity vocabulary. So, the V in Euler's formula is the number of vertices, which in triangulation talk we've been calling n, the total number of points. The number of faces is the number of triangles plus the one on the outside, right? So if we're only counting triangles, we ignored that extra face that fills up the outside of the world. So total number of faces is going to be t plus 1. Then we need to count the edges. So let's look at one of these triangle pictures again. Every triangle has 3 sides, right? So if I look at, I've got 5 triangles. Every triangle has 3 sides. That gets me up to 15. That's too many. What went wrong? Yeah, we counted a bunch of those edges twice, right? Okay. How do you sort out which ones you've counted twice and which ones you haven't? Well, the ones along the edge you didn't count twice. Okay, so let's come back over to this and see if we can figure out what we did. If we look at 3 times the triangle plus k, well, okay, k is the number of points on the convex hull. If there are 5 points on the convex hull, how many edges are on the convex hull? 5, right? If you've got 5 points, it takes 5 edges to connect them up. So, okay, 3 for each triangle, plus the ones around the outside edge. Now we've counted everything twice, so divide by 2. So coming back over here, or thinking back to these guys, 3 edges for each triangle gets us 15, plus count the ones on the outside one more time, 5 more is 20, divide it by 2, that's our 10 edges. So that should get us the number of edges. Okay, so now we have V, F, and E translated basically into triangulation vocabulary. Plug each of those guys into that V minus E plus F equals 2. Okay, so we've got N minus that number of edges, fraction, plus T plus 1 for the faces equals 2. Then it's just algebra. Now you're just rearranging stuff a little bit. So to figure out a formula for the number of triangles, solve for T, and you get the thing that the theorem says. Take that T and plug it into the equation up there for edges, and you get edges in terms of N and K. All right. So what does this mean for Ingress? It means we've answered our question, or at least the one that we started off with. We said if we have a particular number of portals arranged in a particular way, what's the maximum number of links we can make there? Well, you need to know how many portals there are total. You need to know how many there are in the sort of shrink-wrap the cluster boundary. And that'll tell you how many links it'll be. And no matter how you link up that cluster, if you get to the point where everything's a triangle, you will have the same number of links. Okay. And we can even tell you, if you give me those 2 numbers, you can spit back how many links you're going to make. Which is interesting. And I mean, links are great. You get points for making links. But when you really get down to it, what you really want in Ingress is you really want fields. Fields are much more AP. And remember, you're either spreading shaper influence or protecting humanity from shapers. And you do that by putting people under triangles. So we want fields in the game. So what's the best way to field up a cluster? Is it the same answer? Well, first of all, there are 2 questions. And the way the game is scored and the way they run some tally boards, what they really would like you to push for is MU, that mind units thing. The problem is we don't actually know exactly how they calculate it. They tell it to you as if it's adding up all the people inside the triangle. Adding up something over a region sounds just like a Calc 3 problem, right? It sounds like it should be the integral of the portal density, of the population density inside that triangle. It's not. They did something else. What we know that they've done is they factor in the size of the triangle and the population density at the corners. What we don't know is exactly how they weight it by that population density. We also don't know exactly what data set they're using for population density. Census data would make sense. We don't know how fine of a grain they're using for it. We don't know exactly. I have a friend who played some with, there's some websites online that will let you draw polygons on maps and tell you how many people live inside your polygons. What they got playing with drawing some fields and then going out and throwing them was the MU was off by about a factor of 2. But, so there's some potential experimentation to go on in there and figure out, can we nail down more about MU? But it's a much hairier question. So let's simplify a little bit. Let's just think about AP. No matter how big or small your field is, you get 1,250 points for closing a field. So, if there's a way to get more fields inside a cluster, you're going to get more points for fielding it up. If we go back and look at our triangulations again, the thing that makes this a complicated question, because we've already said every triangulation is going to have the same number of smallest triangles. Ingress lets you overlap. So we don't want to just count the smallest triangles. We also want to count any bigger triangles we make in there at the same time. So this guy over here, you've got 5 fields. The triangulation on that side has 6. You've got the 5 smallest ones, and then the bigger one in the middle that has 3 inside of it. So, how do you count? How do you figure out what's the maximum number of triangles you can make on a point set? So, one thing that comes into play, and these are some screenshots from the game. Here we've got 4 portals, and the best you can do on that is 2 fields. Here we've got 4 portals, and you've got 4 fields there. When you can make a K4 in Ingress, you've got the 3 small ones and the one that makes the outside triangle too. So you get 4 fields that way. So, and I sort of circled around the other way. So we need to think about, how do you also count triangles? Well, when you look at why point set triangulations were generated, the mathematics that people were or the problems that people were studying when they generated that mathematics, they didn't care about this. So there isn't an answer to this question in the literature. We don't know a formula. So what are people doing? There are a lot of people who have basically said, here are some ways to get lots of fields. Basically, and most of them amount to look for K4s in different ways. Okay, how can we make lots of K4s? Because those pack in an extra field for every 3. And people have written some code. They've done some algorithmic implementations for looking at, look at this chunk of the map, in some way systematically go through all the possible ways to link it up, and decide which one is best. So this guy that's Memorial Park over in Riverside. Has the walking path loop, the river's down at the bottom. And this was a year and a half, 2 years ago. There are more portals there now. But if you look at that long skinny triangle that's pointing down towards the middle bottom, there are a lot of fields in there. It is a K4, inside another K4, inside another K4. And so one of the ways people look to make lots of fields is find a spine like that, those 5 portals in a row that are straight enough that the links don't cross when you connect them up this way, and build these nested K4s that way. You go digging around on G+, and I've got at least one link in the last page. People are drawing all sorts of interesting ways to nest portals inside of each other. Because there's only K4s inside of some of those triangles. What if you could get K4s inside more of them? Now, this is basically how people maximize fielding. But this involves saying, I want to get layers, 10 layers, or fields 10 layers deep. Where could I do that? And scrolling around on the map and scouring around looking for a place where they could do it. It's not an answer to the question, here is my configuration of portals. How many fields can I get in there? But this is one of the ways people are handling the question. And actually, one of the reasons that that I took this particular screenshot is you've got layers 4 deep twice inside the park. It's also layered on the other side. It's just a little harder to see. There's also been people who have looked for algorithmic solutions. Most of them are variations on what are called greedy algorithms, which basically it says, make a guess at how to field things up. Draw some links. Then make small changes to try and maximize things, and see if by doing that, overall, we can shake out a maximum. Or the other way to do it is say, find a K4. Grow out from there, doing things as best as you can. And if you do that several times, you're likely to find a maximum. There's a piece of code called Ingress, which someone basically implemented a whole bunch of different ways that you might think about maximizing. The one he was first thinking about is, okay, you get points for creating stuff. The other team also gets points for coming behind you and blowing it all up. Destroying links and destroying fields also wins you points. So is there a balance point between I want to get AP and I don't want the other team to get AP for destroying it? So he wrote a Hamiltonian to maximize that kind of energy and implemented an algorithm that would maximize for that. And then he looked at some other things. What if I just want links? Well, you can now answer that question. How many links can I put someplace? But he wrote it so that the code would find a maximum way to link it. What if I want fields? So it does go through and look at a chunk of the map and say, here is a good way to field it. There are some other ones, various bits of code that people have implemented in various places to look at various things, because, like I said, there are millions of people out there, and it's a wide and diverse community, and there are a lot of people with enough coding ability to throw something together and see what they can do. Some of them are better than others, and a lot of them it is possible to find a sort of pathological example that tricks the algorithm. This wouldn't trick this algorithm, but the idea is, early on in the game, someone found 3 portals that were within the tolerance of the game exactly in a row and linked them together as a triangle. The area of that triangle should probably be 0, and so the MU should be 0. Yeah, the game decided that it failed the entire planet and assigned the largest random integer in the memory of the server as the score for that field. Broke the game for a couple hours. So these just very elementary coding ways of approaching things can be broken if things go about it the wrong way. There have been interesting things. So there is an Intel map that shows the entire world and all the portals of various levels that you can scroll in and out of so that you can plan, but you can also see the whole world. And a group of players made a bunch of fields that went over the North Pole, which kind of messed up the way that the rendering of the map. So there have been various things that have broken things in various ways. So all of these are interesting, but they still don't answer our question. Our question was, how many fields can I make? Is there a way to quantify the number of fields given a configuration of portals? It's obviously going to take more than just the number of portals. It's going to take more than the number of portals on the edge and the number of portals not on the edge, right? Because those two triangulations we've been looking at have a different number of fields in them. But is there enough information that we could say, oh yeah, you could get 17 fields there? Or not? Is this something that we can't put a formula to? We don't know, the literature doesn't know. It hasn't been done. I think it's a tractable problem, and if you think it would be an interesting one to come look at, come talk to me. Maybe an easier question, but also not totally answered. And again, sort of going from the other side. Okay, we know if you have 3 portals, you can make 1 field. With 4 portals, the most you're going to be able to make is those 4 fields when you arrange it in a K4. Is there a formula for that? Is there a formula for how many fields you could make on 10 portals if you could arrange them however you wanted? So again, the overlapping parts make it something that isn't out there yet, but could be interesting to look at. And then the other thing that people would desperately like to know, but again, I think this one's probably harder to answer without access to the server-side stuff in Ingress, is can we come up with a better way to figure out the mu of something? Because right now, you can plan a giant field and you will have no idea how much mu it's worth until you've thrown it. Like I said, we know what helps. Bigger fields have more mu than smaller fields. Putting the corners in population-dense places helps. You could crowdsource the generation of the data set. Here are the 3 corners I threw, here's how much mu I got. Here are the 3 corners I threw, here's how much mu I got. But analyzing that, the data set hasn't been generated formally, and no one's really poked around at that either. Are there any questions? And obviously that is not necessarily the main point of Ingress, but it's the interesting mathematics that's popped up. That's my email and my collaborator's email.